This is lecture 24. So in last two lectures, we have discussed what is Nyquist stability criterion. That means if we have that information regarding that loop transfer function poles, and if we know that how many encirclement is there in counterclockwise direction about that -1 J0 point, and if they are same, that means n is equal to p, so then that z would be equal to 0, that means that closed loop system would be stable. So the important thing that we have already discussed, that means using Nyquist stability criteria, we can find that how that closed loop system would be stable. But one more thing we can also see from this Nyquist stability criteria, that is that relative stability. That means if a system is stable, then how much stable it is. That means if there is any perturbation or anything appears to that system, whether that system would be unstable or it is on the verge of instability or not. So to get that information, we need to quantify, that means that stability notion, that is how much stable it is. So that stability, that relative stability is quantified by two terms, that is that gain margin and phase margin. So today we will be discussing what is gain margin and what is phase margin. So first let us start what is gain margin and phase margin. That is what is gain margin and phase margin. So this gain margin and phase margin give us a quantitative measure about that stability. That means if a system is stable, then how much stable it is. So that can be obtained from that gain margin and phase margin. So let us first draw a part of that Nyquist diagram. So this is that GH plane. So that means this is that real part and this is imaginary part. And here this is that GH plane. So then suppose this is that Nyquist. This is that part of that Nyquist plot. So here that omega is increasing and this is that origin, and suppose this is that point which is that critical point -1. So now if we draw a unit circle passing through this -1 point, that means center at origin, if we draw one unit circle, so this is one unit circle. So then what we can see, that this is a point, we can see here that this is a point and this is another point, and we know that this particular axis, this is that -120 degree axis and this is that 0 degree axis. So this is that particular frequency. So this is one frequency. So suppose this is W1, omega 1, and this is omega 2. So at omega 1, this Nyquist plot cuts that unit circle. Means if we just draw a vector like this, and at this particular frequency, that is at omega equal to omega 1, that GH of J omega 1, so its magnitude would be equal to 1. So that means at omega equal to omega 1, if we just find the magnitude of that loop transfer function, it would be equal to 1. And let us see what happens whenever it crosses that -180 degree axis. That means that negative side of that real axis. So at omega equal to omega 2, it crosses that. So this is that point. So it crosses that negative real axis. And if we find that phase at this particular frequency, that is j omega 2, so from it is clear that at omega equal to omega 2, the phase would be equal to minus 180 degree. So these are the two frequencies and these are the 2 points from where we'll be able to get the measures of stability. The reason is, from the Nyquist stability criterion, we know that the closed loop system would be stable whenever the number of encirclement would be equal to the number of poles of the open loop transfer function in the right half of that S plane. So here, if in any case, if this Nyquist plot, if it encircles that critical point, that means if this Nyquist plot is very close to that critical point, so then the number of encirclement would be different if we give a little bit perturbation to that system. So suppose if we just change the gain of that system, then what happens? A particular gain, if we just increase that gain of that system, it would happen that at a particular value of that gain, that Nyquist plot would be passing through that critical point. So whenever it is passing through that critical point, it indicates that the system would be on the verge of instability. So if we just increase that gain further, then what happens? This plot will be shifted towards left. So then there would be one encirclement of that critical point. And whenever there is one encirclement of that critical point, then you can see from the Nyquist stability criteria that N and P would be different. That means that system, closed loop system, would be unstable. So these 2 points, that means at omega equal to omega 2, this is that point, at omega equal to omega 1, this is another point. So these 2 points actually would tell us that this Nyquist plot is how far it is from that critical point. And it is always expected that if that Nyquist plot is far away from that critical point, then even if there is some uncertainty or perturbation, it would not encircle that critical point. That means that number of encirclement around that critical point remains same. So let us see what we can have here. So one thing is that this is that gain. So that means this is a frequency at omega equal to omega 2, and at that frequency, if we just calculate the phase, that phase would be minus 180 degree. So now what would be the gain? So here that gain would be Gj j omega 2. So this is that gain at this particular point. So now if we multiply that loop transfer function by the reciprocal of this gain, so that means gh j omega 2 into 1 by gh j omega 2. So then that gain would be actually 1. So whenever it is 1, what happens? This Nyquist plot will be passing through that critical point, and when it passes through that critical point, that system would be on the verge of instability. So this is a measure. That means this Nyquist plot, how far it is from that critical point. That means if we take that reciprocal of this gain, it tells you that how far it is. So that means if this particular value is very small, suppose 0.1, so then its reciprocal would be 10. That means if we multiply that loop gain with a 10, so then only that system would come on the critical point. That means that system would be on the verge of instability. Similarly, we can see here at omega equal to omega 1, if we find that angle, suppose we get that angle, say this is j omega 1. So if we can calculate this angle at omega equal to omega 1, then we can see that if we add this angle, that is theta, so then this particular point would come to the critical point. So that means that system would be marginally stable, on the verge of instability. Repeating. So at omega equal to omega 1, if we calculate the angle, so then we can see that with this particular angle, if we add this theta, then it would come to the critical point. So this particular angle is also indicating that Nyquist plot how far it is from the critical point. So it also gives us that information. If the system is stable, then how much stable it is. So that means that theta is actually known as phase margin, and the reciprocal of this gain is called gain margin. And the frequency, this omega 1 is that frequency where that Nyquist plot, its magnitude is equal to 1. So that means this is called that gain crossover frequency. This is gain crossover frequency, abbreviated as GCF. So that means that frequency where the gain is equal to 1, that is that gain crossover frequency, and omega 2 is called that phase crossover frequency. So that means that is the frequency where that phase is equal to minus 180 degree. So this is that point. So this is abbreviated as PCF. So let us give that definition. So I think from here it is clear what is that gain crossover frequency and phase crossover frequency, and how that gain margin and phase margin would give us that indication. That means if a system is stable, how much stable it is. That means we would have that relative stability concept. So let us write that formal definition of that gain crossover frequency. That is that gain crossover frequency. So gain crossover frequency, so abbreviated as GCF. So what is that? The frequency at which if we find that gain, that means Gj omega loop gain, that would be equal to 1. So in this figure, W1 is that gain crossover frequency. You can see that at W equal to W1, this Nyquist plot actually crosses that unit circle, and as it is unit circle, that means this radius is equal to 1. That means that gain would be equal to 1. So then what is phase crossover frequency? So phase crossover frequency, it is called PCF. So this is that frequency, the frequency at which the phase, that means we have that loop transfer function, that phase would be equal to minus 180 degree. That means this is that frequency where it crosses that negative real axis that we have discussed here. That negative real axis is actually minus 180 degree point, and here we have seen that W equal to W2. So this is that point where it crosses minus 180 degree, and this frequency is called phase crossover frequency. Now we have seen that at phase crossover frequency at W equal to W2, if we find that what is that gain, and if we multiply that gain with the reciprocal of that one, that means 1 by GH j omega 2, if we multiply that loop transfer function with the reciprocal of that gain, and that gain obtained at phase crossover frequency, then what happens? That Nyquist plot would pass through the critical point. That means that system would be on the verge of instability. That means this is the gain. If we multiply that loop transfer function, then that system would be marginally stable. If we increase further, then that system would be unstable. So this particular gain is called that phase gain margin. So let us write that gain margin. So gain margin, it is abbreviated as GM. So what is that gain margin? The gain margin is the reciprocal of the magnitude is the reciprocal of the magnitude. What is that magnitude? That is GH J omega, and that omega is at phase crossover frequency at PCF. So the gain margin is the reciprocal of the magnitude at PCF, phase crossover frequency. So this is written as that Kg. So Kg is that reciprocal of this one, and this one would be that phase crossover frequency here. That means that gain calculated at phase crossover frequency, if we take that reciprocal of that, it gives you that gain margin. So in dB scale, if we take it in dB, so dB it would be 20 log kg, and this one is minus 20 log gh j omega PCF. And from here you can see that this gain is less than 1, and when it is less than 1, so basically that would be negative. That would be negative. This value is negative. Log of that value 0.1, 0.2 like that, that would be negative. So basically negative, negative, it would be positive. So in case of stable system, that gain margin is always positive, but that gain margin may be negative if it is a non-minimum phase system. That means if it is unstable, or if it has some 0 on the right half plane, so you may have that negative gain margin. But in case of stable systems, you have that positive gain margin. So now let us see what is phase margin. So phase margin is abbreviated as this one, PM. So here at omega equal to omega 1, if you calculate that phase, that means at omega equal to omega 1, that is actually that gain crossover frequency. Whenever you calculate that gain, it would be equal to 1, and the amount of phase, so this is that phase, that theta. If you add that phase to that loop transfer function phase, then that system would come on the verge of instability. That means that phase, that extra phase lag tells you, that means if you add that much of phase to that loop transfer function has phase lag, then that system would be marginally stable. That is, that Nyquist plot will be passing through the critical point. So let us see the definition. The amount of additional phase lag, that is that theta, additional phase lag at the gain crossover frequency, at the gain crossover frequency. So that means the frequency at which it crosses that unit circle required to bring the system to the critical point, and to the critical point means to the verge of instability. So here we have seen that the amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of instability. So here you can see that is, this is that theta. So that means if you add this theta to that gain, that means the gain that you have obtained at gain crossover frequency, if you add it, then this Nyquist plot would come to that critical point. That means it would be on the verge of instability. So this is called that phase margin. So how can you quantify that phase margin? So this is phase margin. Phase margin is equal to 180 degree plus that angle GH J omega, and that omega is at gain crossover frequency. So basically at gain crossover frequency, in case of stable system, we can see that this phase angle, say suppose this one is say 135 degree. Suppose this is minus 135 degree. So if it is minus 135 degree, you can see it here. If it is minus 135 degrees, so suppose this is minus 135 degree. So then 180 minus 135, that is 45 degree. So if you add 45 degree more, so then that point would come to that critical point. That means it would be on the verge of instability. And this particular angle, 45 degree, in this case, it is that phase margin. So whenever you have a stable system, then you have that positive phase margin, and the case that we have done, it is for that positive system. And then we can see that what is that expected value. That means whenever we will be designing a closed loop system, then we understand that this gain margin and phase margin would tell us that relative stability of that system, but how much gain margin and phase margin should be there. That expected phase margin is 30 degree to 60 degree, and gain margin would be greater than 6 dB. So this is that expected one. You may ask why, from where we get this data. So later on you will see that if you can maintain this much of gain margin and phase margin, then that system would be stable, as well as it would be robust stable in some cases, and the performance also would be satisfactory. So you should keep remembering these two data. That means what is that expected gain margin and phase margin. So gain margin is expected to be greater than 6 dB, and phase margin it would be in between 30 to 60 degree. So if we just make that phase margin very high, so that means it is more than 60 degree, then that is also good. But in that case, we need to see that, okay, phase margin is very high, but gain margin is very poor. It should not be the expected one. That means gain margin and phase margin, you need to make a trade-off between these two quantities. So now one important thing we are going to discuss, that is this gain margin and phase margin also can be obtained from Bode plot. So let us see how to find it. So that is gain margin and phase margin. Gain margin and phase margin can be obtained from Bode plot. So how to get that one? So let us first draw the Bode plot. So in Bode plot we have that two axes. So one is that gain, another one is that phase. So this is in this is that rad per second. So this is log omega rad per second, and here also we have that rad per second logarithmic scale, and here we have in dB magnitude, and here we have in degree. Suppose we have that plot like this. Suppose you have a plot like this, that is that gain plot, and we have, suppose this angle is 180 degree, and this is that 0 dB line. Suppose we have that plot like this, that is that phase plot, and this is for stable system. And here we can see that, so this is that point where that magnitude plot crosses that 0 dB line. So crosses that 0 dB line means log 1 equal to 0. That means that gain is equal to 1. So that we have seen, whenever that plot cuts that unit circle, that means that gain is equal to 1. That we have seen here, omega equal to omega 1. And so that frequency is that gain crossover frequency. So here this is that frequency when that magnitude plot crosses that 0 dB line. So this is actually that gain crossover frequency. Gain crossover frequency. And we have seen that at gain crossover frequency, what is that phase? And if we subtract it from 180 degree, then that would give that phase margin. So let us see here. So this is that frequency, and we can see that the phase is this one. So this much of phase you have at omega equal to omega 1, that means at GCF, and this is that angle if we subtract it from that 180 degree, so then that is that phase margin. So we can see that how to get that phase margin from Bode plot. So first we see where it cuts that 0 dB line. That means this is the frequency where the magnitude of that loop transfer function is equal to 1. That means this is that gain crossover frequency. We first find at gain crossover frequency what is that phase. Suppose this is, for example, say suppose this is 135 degree, and then 180 minus 135 degree. That means how much angle if we just add here such that it would be minus 180 degree. So that would be actually 45 degree. So that's why in this particular case that phase margin is 45 degree. So now what is that gain margin? We have seen that in case of gain margin, we need to first calculate what is that omega 2. So omega 2 is that phase crossover frequency where it crosses that minus 180 degree axis, negative real axis. So here we can see that this is that frequency. Here we can see this is that point where it crosses minus 180 degree. So that means this is that frequency, that omega 2. So omega 2, so this is actually that phase crossover frequency. And at phase crossover frequency, if we just take that reciprocal of that one, 1 by j omega 2. So that means here we can see that from Bode plot. So this is that value. That means if we just add to that one, so then it would be equal to 0 dB. That means that gain would be equal to 1. So this is actually that gain margin. And here we have shown it for stable systems, and both gain margin and phase margins are positive. So these all are the positive gain margin and phase margin. So positive gain margin and phase margin. So positive gain margin and phase margin means it is stable system. So whenever we check the stability, so from Bode plot also we can check stability. That means if it is minimum phase system, then if it is a positive gain margin and phase margin, so then it is stable system. And so what we have discussed so far, we have defined that what is gain margin, phase margin, and gain crossover and phase crossover frequencies, and how to define that gain margin, phase margin from Nyquist plot. And then we have shown that gain margin and phase margin can also be obtained from the Bode plot. So now there is one question. So it might happen that in a Nyquist plot, so you may have multiple gain crossover frequencies and phase crossover frequencies. Then what happens? So if you have multiple GCF, gain crossover frequency, and PCF, then how to handle that situation? So that multiple gain crossover frequency, so first we just consider that multiple phase crossover frequency. So if you have that multiple phase crossover frequencies, suppose we have, so phase crossover frequencies means it would cut that. So suppose we have this type of plot. So we are just showing a part of Nyquist plot, and of course that is that GH plane. This is that real axis, and this is that imaginary axis. And suppose you have that critical point here. So we have three frequencies here. That is that omega 1, omega 2, and omega 3. And then we can see that there are three frequencies where that Nyquist plot cuts that minus 180 degree axis. So that means you have multiple number of phase crossover frequencies. So then what would be the case in this case? You can see that if we change the gain, so if we change the gain, that then what happens? This particular point may shift towards that direction. That means if we start increasing that gain, so this point also will be increasing, will be shifting towards left, and this one also will be shifting towards left. So at a particular gain, this plot will be passing through this critical point, and after that it will cross it, and whenever it crosses that critical point, then the number of encirclement will be changing. Then again, let us see if we start decreasing that gain. So if we start decreasing that gain, so all those points will be moving towards right. That means we are decreasing that gain. So then at a particular value of gain, you will see that this particular point would come to the critical point. And again, if we decrease that gain, so this particular point will be crossing that critical point. So whenever this one would cross that critical point, then again the number of encirclement will be changing. So this is a case where that gain K is actually restricted from upper side and lower side. That means if we increase that gain beyond some value, then again that encirclement, number of encirclement will be changing, and if we decrease it and if we go beyond some value, then again the same thing would happen. So this is actually the case of conditionally stable system. So conditionally stable means we cannot increase or decrease that gain up to some value. That means if we increase that gain up to say infinity, so in some cases it happens, so if you have a first order system or second order systems, it happens like that. But in this case, we can see that gain can be varied only in some range, that is from K1 to K2. So this type of system is called that conditionally stable system. Whenever you have that multiple number of phase crossover frequency. So now let us see, whenever you have multiple number of gain crossover frequency, then how to handle that situation. So again, that is that real axis, and this is imaginary axis, and this is that GH plane. And suppose we have drawn one unit circle because we need to find that gain crossover frequency. So this is that point, this is that point, that is that critical point. And suppose your plot is like this. So here we can see there are 3 points. So this is one point, this is one point, and this is another point where it crosses that unit circle. So this is that unit circle. So unit circle means at those frequencies, so those frequencies are suppose omega 1, omega 2 and omega 3. So there are 3 frequencies where that magnitude is equal to 1. So that means you have multiple number of gain crossover frequencies. So in this particular case, we need to consider only omega 3, which is closer to that critical point, and we'll take that this theta as phase margin. So whenever you have multiple number of frequencies, the gain crossover frequencies, that means where it cuts that unit circle, then we need to consider that highest frequency. So here actually frequency is increasing like this, and whenever omega is tending to infinity, it is coming to that 0. So this omega 3 is that highest frequency which is closer to that critical point. So at that particular point we will be calculating that phase margin, and it gives you that relative stability information. So here we have discussed 2 things. That means whenever you have multiple number of gain crossover and phase crossover frequencies, whenever you have multiple number of phase crossover frequencies, then this is actually that conditionally stable system. That means we can vary that gain only in some range. And whenever you have that multiple number of phase crossover gain crossover frequencies, so then we need to consider that frequency which is cutting that unit circle, and it is that closest to that critical point. So at that particular frequency we will be considering what is that phase margin, and it gives us that relative stability information. So now we are going to discuss one more concept, which is called the delay margin. So what is the delay margin? We have already discussed what is that transportation lag. So now let us discuss what is the delay margin. So we have discussed what is gain margin, what is phase margin, and now The delay margin is very important concept, because whenever we design a closed loop control system, so in every closed loop system there is some sort of delay. So now the delay margin tells us that how much delay can be introduced to that loop so that that system remains stable. That means it gives us a margin, and if we introduce a delay more than that margin, then that system would be unstable. So you may ask why it is becoming unstable, because already we have shown in the Bode diagram. That means whenever there is some transportation lag, if we draw that gain and phase plot, then we have seen that gain remains same, gain remains unchanged, because that gain of that e to the power minus tau j omega, it would be equal to 1, but it continuously contributes some phase lag to that system, and whenever it contributes that phase lag, then that phase margin would be reduced, and if you keep on increasing that delay in that loop, then after some time it would be unstable. So the delay margin is actually indicates that what is that margin up to which that system remains stable. So let us first derive that what would be that delay margin. So whenever we have a closed loop control system with loop transfer function Lj omega, so then that characteristic equation becomes 1 plus Lj omega. So L is that loop transfer function, so this one is equal to 0. But whenever there is some delay, so delay means there would be one exponential term that we have seen, e to the power minus tau s. So e to the power minus tau s. So now we are discussing that frequency response, so that means at s it would be j omega, so that one would be equal to 0. So this is that characteristic equation. So whenever there is no delay, so this term would not be there, but whenever there is some delay, the characteristic equation would be this one. So now we can see from here that with delay term e to the power minus tau j omega, so this one is equal to minus 1. So now this is that equation, and we get it from the characteristic equation, and it is a complex equation, so immediately we can write what is that gain and phase equations from corresponding to this equation. So then the phase is Lj omega, that means this is that phase of this one, minus for this one that phase contribution we have seen that it is minus that omega tau, and omega tau is in radian. So if we want to write it in degree, that would be 180 degree by pi. We have already discussed it in that Bode plot lecture. So there you can see that means this is that phase contribution. That means if we take cos of j omega plus j of sine j omega minus j of sine j omega, and if you take the tan inverse of that, it would be that omega tau, and that is in radian, and here I have written in degree, so that's why I have multiplied with 180 degree by pi, and as it is minus 1, so it is 180 degree. So this is that phase relation. And what is that gain relation? That means if you take that mod of this one, so it would be L j omega mod of this one equal to 1. So now one interesting thing we can observe here, that this is that frequency where the magnitude is equal to 1. So that means this omega is nothing but this is gain crossover frequency, because this is that frequency where that gain is equal to 1. So that means whenever we multiply with that one, so you can see that gain crossover frequency remains same. So we are just indicating that gain crossover frequency by omega g. So then we can see that, so that angle criteria also will be fulfilled at gain crossover frequency. So that's why I have written that omega g here. So now if you look at that phase margin definition, so here you can see that phase margin is equal to 180 degree plus angle at gain crossover frequency, loop transfer function. This is GH is the loop transfer function, what I have mentioned here there, L by L. So here we can write we know that from the definition of phase margin, that phase margin is equal to 180 degree plus that angle of L J omega G. Omega G is the gain crossover frequency. So now you can write that L J omega G, this is that angle equal to phase margin minus 180 degree. So now if I replace this one here, so then what will we get? So if we replace it, we will get phase margin by 180 degree minus we have this term, that is omega G tau 180 degree by pi equal to 180 degree. So now if you bring this minus 180 degree to that right, so then 180 that would be 360, that is nothing but 0. So here we can have that relationship that phase margin is equal to omega G tau 180 degree by pi. So here you can see this is that tau, this is the tau, this is the delay. So what would be the delay here? So we can see here the delay would be equal to phase margin divided by omega G into pi by 180. So that means if we introduce this much of tau, so then that system would be on the verge of instability, and this is that range. So for a particular closed loop system, if we know that it has that much of phase margin, and if we know that this is that gain crossover frequency, so from here we can estimate that how much delay can be tolerated in the closed loop system without hampering that stability. So from this particular concept, that is the delay margin, one thing we have understood that if we increase that omega G, that means if that gain crossover frequency is increased, then later on we will discuss that when omega G is increased, then bandwidth will be increased. So bandwidth is increased means that system becomes fast. But in turn, what happens if the system becomes fast due to that increasing of that omega G, we can see that this delay margin will be reduced. That means if we introduce a small delay to that system may be unstable. So we should be careful about that. We should not make that omega G gain crossover frequency or bandwidth very high. Or we can do also one thing, that means in that case we can increase that phase margin. Again, we need to see that whenever we are increasing phase margin, then what would be the gain margin. So we need to just make a trade-off between all these things, and we need to keep those things in mind that these are the relationships. So now, so let us see what we have discussed so far. That means we have discussed three things. One is that gain margin, phase margin, and delay margin, and they actually tell us that relative stability of that system. So now we are going to discuss one more concept. That means whenever we have studied that first order and second order system, that is time domain analysis, there we have seen how to characterize that system, or how to define the specifications of that system, and it is defined in terms of that percentage of overshoot, or settling time, or delay time, or peak time, or damping ratio. So those terms are actually the time domain specifications. That means whenever we want to specify something in time domain, it is characterized by those terms. And in frequency domain, we have seen, that means to indicate that stability as well as that performance, we need to characterize those things in terms of phase margin, or delay margin, or gain margin. So phase margin, gain margins, those are actually coming from that frequency response, and that percentage of overshoot, settling time, etc. are coming from the time response. So now we are going to discuss, that means what is the relationship between this time response and frequency response specification, and we will be doing it from the closed loop Mind that we are just going to discuss with the closed loop frequency response. So far what we have discussed, those are actually frequency response of the loop transfer function or open loop transfer function. So now I am going to show the relationship in between that time domain specification and frequency domain specification based on the closed loop frequency response. So let us give that heading, that is that relationship with time domain analysis. That means what is the relationship in between the time domain and the frequency domain, and here that frequency domain we are doing it for the closed loop transfer function. So here we can see whenever we have that loop transfer function, that is omega n square by s plus twice zeta omega n, and if we close that loop, so then we have with negative feedback, this is that reference comment and this is that output. So what is that closed loop transfer function? That ys by rs, that would be in standard normalized second order transfer function form, that is 2 zeta omega n s plus omega n square, and we have seen that this particular thing is characterized by these two terms, that is zeta and omega n, that is that natural frequency and damping ratio. So now we are going to discuss, that means how those time domain specifications are related with the frequency domain specification, and here that frequency domain means we are doing it for that closed loop frequency response. That means whenever this transfer function is given, so this transfer function means this is a closed loop transfer function, second order closed loop transfer function from input to output. So then in Bode plot we have seen that if we do the frequency response for a second order term, then how it looks like. So in normalized form, say suppose it goes like that, so that means it is in the denominator. So there would be a peak, and this peak depends on that zeta value. We have already seen that one. So that is that logarithmic scale, say log, if we just take it in normalized form, if we take it as normalized form, then we have seen that that is okay, so we take it in that log omega form. Okay, so that means there would be that natural frequency, that corner frequency would be omega n, and whenever we vary that zeta, then we have seen that there would be a peak. So this peak is called that resonance peak. So this peak is called that resonance peak, and we have seen that this peak depends on that zeta value, and this peak, actually resonant peak, it occurs. So resonant peak occurs when that zeta, that means that damping ratio is less than equal to 0.707. So here one thing, you should not be confused with that percentage of overshoot. That overshoot is actually appears in time domain, and here we are talking about that resonant peak, which is in frequency domain. So that is that magnitude versus frequency in logarithmic scale, and this peak is called that resonance peak. So now this is that magnitude, and this particular magnitude is called that MR, that is that resonant peak. So this resonant peak actually indicates that what is your damping ratio, and it also tells us, that means it gives us some information about that relative stability. So that means if MR is very high, then that zeta value is very small and its stability is also very small. So let us see, that is that maximum peak, again I am telling, so this peak is in the frequency domain, and we are discussing that closed loop frequency response. So the maximum peak in Bode plot, so here the Bode plot, what we have done, it is for that closed loop transfer function occurs at, so this particular frequency, that is actually omega r. So this is actually not that natural frequency. So this particular frequency is called that resonance frequency. So this resonant frequency is related as 1 minus 2 zeta square. So this particular frequency is called that resonance frequency. And this frequency is not that natural frequency, and this is that relationship. So whenever we do that Bode plot, we will get that one. Then what would be that maximum peak? So this maximum peak, that is that MR. So MR is twice zeta 1 minus zeta square. So I am not just going to show any derivation, so it can be done easily. So resonant peak, so this is that peak, this is that resonant peak, this value is MR. So now this particular value, that MR, also tells us that large MR, that means whenever peak is very high, we have seen that it indicates the damping is poor. That means the damping ratio is small, damping is poor. We have already seen it. So expected MR, so that means whenever we will be designing that closed loop system, that expected MR is that MR should be less than equal to 1.4 to 1. So, and here we can see that, so that is greater than 1. So that means we can see here this MR, that means that peak would not appear if that zeta value is greater than 0.707. So you should not be confused with the time response, because in case of time domain, the overshoot does not appear whenever that zeta is greater or equal to 1. That means whenever it is critically or overdamped, there is no overshoot, but that zeta is greater than 1, equal to 1. And here this zeta value is 0 to 0.701, and we are discussing about that frequency response. So this is not time response. So you should not be confused with that. And there is one interesting relationship is there. That means whenever that zeta is in between 0.6, then zeta is approximately equal to that phase margin by 100. So whenever we will be designing a closed loop system, so these information are very much essential as well as very important. So suppose it is said that you need to design a controller so that your phase margin would be 45 degree. So then from there immediately you can understand, if it is phase margin 45 degree, so it is a second order system. So then the zeta value would be around 0.45, because 45 divided by 100. And that zeta actually works whenever zeta in between 0 to 0.6. And for small value of zeta, so that means whenever zeta is small, you can see here that the resonance frequency is omega n into 1 minus 2 zeta square. And what is the damping frequency? The damping frequency that you have seen in time domain analysis, that is omega d equal to omega n into square root 1 minus zeta square. So whenever this zeta is very small, so then almost that resonance frequency and that damping frequency, they are almost same. So that means for small value of zeta, that omega d and omega r, that resonance frequency, are almost same. So you should remember these relationships, and it would be very much required whenever we will be designing or analyzing that system, closed loop system. So let us discuss one more concept, which is called that bandwidth of a system. So this is that bandwidth. What is that? whenever we draw a Bode plot, so suppose we are drawing a Bode plot, so here, so suppose for closed loop systems we have drawn a Bode plot, and that plot appears like this. So this is that plot, and then we can see that, say suppose this is that 0 dB line, and here you have that log omega. So then what happens if we take a particular value? So here suppose this is 3 dB, that is 1 by root 2 log 20 log, that one 1 by root 2. So then if we just draw this line here, then we can see that this is that frequency, where this is that frequency. So in this particular frequency range, we can see that the magnitude that we have at 0 frequency, so that magnitude falls below the minus 3 dB line. So that means after that frequency it falls below the minus 3 dB. And in this particular frequency range, the gain is above minus 3 dB. So this particular range is called that bandwidth. So the formal definition of bandwidth is as follow. So the frequency range. So here what is that frequency range? That is 0. So whenever you draw the Bode plot, so then this frequency is actually tending to 0, so 0.01, 0.001 like that, it is in log scale. So the frequency range, that is omega less than W bandwidth and greater than 0, in which the magnitude of the closed loop, so here we have shown the frequency response of the closed loop transfer function. Closed loop does not drop minus 3 dB. So minus 3 dB, that is 20 log 1 by root 2. 3 dB is called the bandwidth of the system. So bandwidth of the system means it is the range of frequency above which the gain is minus 3 dB, above the minus 3 dB. So now the question is, why it is important? The reason is there is a relationship between that rise time and bandwidth. So rise time, we have seen in the time domain response that rise time, we know that means how much time it takes to reach that 10% to 90%. That rise time is inversely proportional to the bandwidth. So what we have seen, that means if the bandwidth is increased, then the rise time will be decreased. So rise time is decreased means the system becomes fast. And here we can also see that means whenever the bandwidth is increased, so this is actually that minus 3 dB line. So that means if we just increase that gain, this particular plot would be shifting like this. So whenever it would be shifting like that, so this one would be actually the minus 3 dB line, and we can see that the frequency, the range, this WB range is increasing. So that means if we increase the gain of that loop transfer function, then the bandwidth will be increased, and whenever the bandwidth is increased, so then that system would be fast. But again, if we increase, if we make that system fast, then there would be a problem. So we can see that its phase margin would be reduced. So basically, whenever you will be designing a system, you need to take care of all of those things, and you need a good trade-off between those quantities. So today, what we have discussed that what is gain margin, phase margin, and what is gain crossover frequency, phase crossover frequency, what is the delay margin, we have discussed, and how to find that gain margin and phase margin from the Bode plot. And if you have multiple gain crossover frequency and phase crossover frequency, how to handle those situations. In one case it would be conditionally stable system, and in another case you can find that phase margin, and what is the delay margin, we have seen that. And here we have established some relationships between the time domain analysis and that frequency domain analysis, and finally we have given the definition of bandwidth. So today I have completed my part, and after that break Professor Ghosh will be taking that design part. Whatever you have learned so far, that starting from that modeling, then time domain analysis, then Rautha-Ridge criteria, then root locus, Bode plot, Nyquist plot, frequency domain analysis. So all of those concepts will be exploited for designing a compensator or controller. Thank you very much.